so 8.3 is on trigonometric integrals. And so you see the title of this section and you're like, well, what the heck? I know how to integrate trig integrals, or at least I have seen people do them in the past. So what's different in these trig integrals than what I've done before? Yeah, maybe it should be called tricky trig integrals. The main thing that we're going to learn out of this section is that we can integrate things like sine to the m of x times cosine to the n of x power, where m and n, where either m or n is a positive integer. So think about an integral that has sine to some power and cosine to some power, and one of those has to be a positive integer. We can also integrate things that are integrals that are in the form secant to the m power times tangent to the n power. All right, so we're able to do that because we can rewrite the integrand in a way where we will have a u and a du present. That's what integrals are all about, right? U and du. Unless they have a special formula, they're all about u and du, having the du present. And so sometimes we can manipulate the integrand a little bit and bring the du out to the side and then have the u and du present. And I'll show you how we're going to do that. Now, we're also going to have to use a few trig identities. So one trig identity that we will have to use is sine squared x plus cosine squared x equals 1. We all know that one, right? Yeah. Another one that we'll have to use is the alternate form of the half angle formula. So if you took me for trig, you know we went over half angles, that there were two formulas on the formula sheet. Even if you didn't take me for trig, you have a trig formula sheet from me. So those alternate forms, they're in the very top right-hand corner on the side of the formula sheet that has the small unit circle. They are sine squared x equals 1/2 times 1 minus cosine 2x, and cosine squared x equals 1/2 times 1 plus cosine 2x. Now, as far as integrals are concerned, those are two of the most powerful formulas that trig formulas that we cover. Because look what they do to an integrand. If we have an integrand that's sine squared or cosine squared, they allow us to take something to a second power and change it over to a constant and something to a first power. And so with integrals, that's a big deal. Because with integrals, you always have to have the du if it's raised to a power, or it's under a radical, or it's a product or something like that. So the reason why you can't just straight up integrate sine squared, it's not cosine squared. The reason is the u would be sine squared, so you would need a cosine. I'm sorry, the u would be sine, so you would need a cosine present. Well, if you rewrite it like this, then we just have two easy integrals. We have an integral of a constant, and we have the integral of a trig function to the first power. Those are two easy integrals. So those two formulas, there's a couple of different ways things that they're called. Some people call them the alternate form of the half-angle formula. I have always called these, and it's not just me, I've seen it in textbooks, the power-reducing formulas. Because they reduce a power, they take a square and they make it into something to the first. Now, with other trig stuff that we do, maybe if we're doing identities, that's not that big of a deal, but with integrals, even not with derivatives, that's not that big of a deal. But with integrals, that's a big deal, when you can change a power. Okay. So let's see how we can use the Pythagorean identities or half-angle identities to work integrals in the form of the product of sine and cosine. So let's say that I had the integral of sine to the 2k plus 1 power of x times cosine to the n power of x dx. Now, if that confuses you, what does this term right here, what does this power actually mean? What does that tell you about that number? Plug in any value for k. Any integer for k. I'm sorry, not any value. Any integer for k. Think about the numbers that you get out. Let k equal a couple numbers and see what you get out. Now, what can you tell me about those numbers? I heard someone say they're positive. Yeah, if you let k be positive integers, then you always get a positive something there. What else? They're odd. That's very important. All right. So if the power of sine, this is like you do this on this case. This is case 1. If the power of sine is odd and positive, or positive and odd, then we are going to take one of the sine terms out to the side, and we're going to convert the remaining sines to cosines. So if you like to write that in words, we're going to take one sine of x term out. I guess I can write out to the side. Now that I'm writing it in words, it may not be the best English. And convert the remaining sine terms to cosine terms by using, how do I do that? How do I change sine terms to cosine terms? What formula have we written down up here? We could do that, but it would be very long. So we're going to use the Pythagorean identity. All right. And what's the formula we would use? If we're changing sine terms over, we would use sine squared x equals what? 1 minus cosine squared x. All right. When I take that sine term out to the side, then what will the power of sine that I have, that I took the term from, become? What type of power will it be? It will be positive and what? If you take one number away from an odd number, it becomes even. So that's why we're able to change it over to cosine. Okay? So what's going to happen when you take the sine term and move it over? Instead of having an odd number as a power, you're going to have an even number as a power. And what are we doing? We're taking one sine term out to the side. So I'm bringing sine to the first power out here, always. Now, after I convert all of these sine terms, the sine of x to the even power terms over to cosine terms, then every cosine term will have this sine term out to the side. So every cosine term will have its du out to the side. That is why we bring this out. This term is being saved for the derivative of u, or the du. That is why we actually use this technique. Because bringing a sine out and then changing the sines that we have over to cosines is going to give us all cosine terms. And if we have all cosine terms, that sine on the outside of all of those cosine terms will be the du for every one of them. Let me show you what I'm talking about. Let's say that I had the integral of sine cubed x cosine to the 8th x dx. So according to my rule that I wrote down up here, I need to bring one sine of x term out to the side. I'm going to do that first. So then that'll give me the integral of sine squared x cosine to the 8th x times sine x dx. Now do you see, I can move that out because this right here, these three terms written in a row, and I know I'll put the last one in parentheses. I could put this one in parentheses. I could put this one in parentheses. But it doesn't matter if the parentheses are there or not. We know that that means multiply, 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 right? If you have things written side by side. Now, after you do that, you want to take this term right here and convert it over. So if I converted that over, what do I plug in right here for sine squared x? 1 minus cosine squared x. So I'm going to put that in parentheses. 1 minus cosine squared x. And then that's times cosine of x to the 8th. And you don't have to put it in parentheses, but you can. Times sine of x, the one that I brought out to begin with. Now, take your cosine of x to the 8th power and multiply it times both of those terms. So I have the integral of, what is 1 times cosine of x to the 8th power? Just cosine of x to the 8th power minus cosine of x to the 10th and we have both of those terms times sine of x. Now, why is this the du for both of these? Because what does it mean if I write it there? Now, don't write what I'm about to write because I'm going to erase it. I could multiply this in and write the sine of cosine to the 8th of x, the integral of the cosine of x to the 8th times sine x minus the cosine of x to the 10th times sine x. So I could write that, but that's an extra step that you don't have to write. Because the sine is the du. If we let u equal cosine of x, the du is negative sine. And we can adjust for the positive or negative. Same here. If I let u equal cosine of x, the du is negative sine. So you don't have to write that out like that. That'll save you one step. Okay? And this is just the du for both because it's multiplication here. If this was plus, no, it wouldn't be. But remember, it's multiplication. So it is for both of those. I kind of feel like I'm trying to beat that into some of your heads and you probably get it, but that's a very important concept because we're going to use that same concept to do other things in this section. All right, so now for this integral, u equals cosine x. So du is going to equal negative sine x. And the same for this integral. U equals cosine x, so du equals negative sine x. So for both of this is two integrals, right? Because we're subtracting these terms. So it's two different integrals. Both have a u of cosine of x and a du of negative sine x. But how would I can bring the negative out for both of them at once if you want to. That's fine. But how would I need to rewrite the integrand so that I make sure that I integrate properly? I let u be cosine, so what is this going to be? U to the 8th minus u to the 10th, and then the sine of x is inside the du. So that's what I need to integrate, and then I need to plug my u back in. All right, so this is the negative of, what do I get when I integrate u to the 8th? Not taking a derivative, so u to the 9th over 9 minus u to the 11th over 11 plus c. The last thing to do is to plug my u back in. And I'll distribute my negative just to do it. So that'll be the negative of cosine of x to the 9th over 9 plus cosine of x to the 11th over 11 plus c. All right, questions? All right, so let's say that I had the integral of, now I'm going to throw you two curveballs in this problem. No change-ups, just curveballs in here. Never slows down. Sine of x to the 5th times the square root of the cosine of x dx. And yes, this is two terms, that term times that term. Now, for what we're doing to work out, we only need the power of sine to be odd and positive. We're going to do everything the same, except you're going to see we're going to run into some other stuff we have to do. All right, so that's going to be the integral of, if I bring out a sine term, that's going to be sine to the 4th power. Now, what can I say that's cosine to what power? Cosine of x to the 1/2 power. Now, whether I write the 1/2 on the outside or I write it between the cosine and the x, that means the same thing. And then I've brought out, remember we bring out this magical term, all of this works because we're bringing out a sine of x to the 1st power. And it's eventually going to be the du. Now the problem, the first, I guess it's either first or second curveball, depending on if you have trouble with radicals, is how do I change sine to the 4th x over to something in terms of cosine? And what we have to do to be able to do that, we're going to still use the Pythagorean identity, but we have to think about sine to the 4th like it is sine squared squared. You know, if I was to say sine of x all squared squared, power to a power you would multiply, and that would be the 4th power. And you may be wondering, well, why would you have to do that? Or what would you do next? Well, now we just plug in what we did before for sine squared x. We plug in what? 1 minus cosine squared. Now, I have a squared on the outside of that power, though, so that's important. So how do I square 1 minus cosine squared? I have to FOIL it out. I don't just square the first term and last term. So you need to, if you need to do that over to the side, if you need to say 1 minus cosine x times 1 minus cosine squared x times 1 minus cosine squared x, if you can't do that in your head, then do it over to the side. FOIL it out and combine like terms. And see if you get this. All right, so I fold that out. Combine like terms, I have that trinomial there, times cosine of x to the 1/2 power times sine of x dx. Now what do I need to do? Remember, the sine is going to be the du, no matter what. Well, I say no matter what, but it's going to be the du. I need to take this and multiply this in. There, there, and there. And I'm going to start writing my powers in the middle. I kind of get annoyed when I write fractions on the outside like that. So that's going to be cosine of x to the 1/2 minus 2 cosine of x to the, how do I do that? I don't say 2 times 1/2. I had to say 2 plus 1/2. That's what you do when you multiply like terms with different powers, or with powers, you add the powers. So 2 plus 1/2 is 5/2 plus cosine, what's that going to be? 9/2. sine of x dx. All right. So now, for this integral, or this term, and this term, my u is going to be equal to cosine of x. So my du is going to be equal to negative sine of x. So that's, I bring out the negative. The sign is present. That's why we brought that out. The sign is the du for all three. And now I can rewrite this as the integral of u to the 1/2 minus 2 u to the 5/2 plus u to the 9/2 du. All right, so those integrals are now easy. 2/3 u to the 3/2. So I have negative. I'm going to go ahead and distribute the negative and do the integration. So that's going to be negative 2/3 u to the 3/2 plus, what's that going to be? You're going to multiply by 2/7. So it's going to be 4/7 u to the 7/2, right? Because you have to divide by 7/2, multiply by 2/7. And then that's going to be minus 2/11 u to the 11/2. Do not differentiate there. It's easy to. Believe me, I've done it before. All right, the last thing we have to do is plug in our u. Our u was cosine of x. Any questions? All right, so that's what we do if we take the integral involving sine and cosine and the power of sine is odd. Well, what if it's not? What if the power of cosine is odd and the power of sine is anything else? That is our second case. So if we have the integral of sine of x to any power and cosine of x to the 2k plus 1 power. So what does that mean? That means the power is odd and it's also going to be positive. All right, then we're going to do something very similar. We're going to take out a cosine of x term and save it as the du. And we're going to convert the remaining cosine terms to sine terms. So same thing except for cosine. So the only thing we have to do is remember, when you convert those over, instead of saying sine of x equals 1 minus, or sine squared x equals 1 minus cosine squared x, you'll have cosine squared x equals 1 minus sine squared x. But everything else is the same. There's nothing different. The du will be cosine. So you don't have to bring out a negative because if sine ends up being your u for everything, then your du is going to be cosine. Do I need to work one like that? It's exactly the same, except you convert cosines over to sines. But I don't mind working one if you need me to. Going once. Okay. I feel like you were just about to say, just shut up and do one, but I'll take it like maybe not. All right, here is the integral that we're going to do. Looks a little complex at first, but it's not too bad. The integral of the cosine cubed of x over the square root of the sine of x dx. Yeah, so just bring the sine of x to the top. That'll be, but when I do that, what is that going to make that? Negative 1/2, right? Sine to the negative 1/2. Now I also want to bring a cosine term out, so I'm going to do that too. I'm multitasking. So I bring a cosine term out, so that reduces the power of the cosine cubed to cosine squared. Now we're going to take cosine squared and we're going to plug in 1 minus sine squared. I had to do one of these integrals yesterday in 2 days ago in Cal 4. So, I mean, they pop up every once in a while. We have to start converting things over to polar sometimes. Something will pop up. This polar's lots of trig. I don't know if you've done that in physics yet, but you will. Or mechanics. Alright, so now distribute your sine of x to the negative 1/2 power. So that's going to be the integral of, when you multiply it times 1, that's just sine of x to the negative 1/2 power. Then I'm going to have minus, because there's a minus sign there, sine of x. Now what power does this become? Because that's the second power, that's 4/2 plus negative 1/2 is 3/2. And I'm not going to multiply the cosine in because I brought that out for a reason. That's going to be my du. So for both of these integrals, that's 2 separate integrals, for both of them, u is equal to sine of x, so du is equal to cosine of x. All right. So this is going to be the integral of, how do I write my u notation now? U to the negative 1/2 minus u to the 3/2 du. All right. So now integrate both of those. So when you add 1, that becomes u to the 1/2. So divide by 1/2 is multiplying by 2. So that's 2u to the 1/2. Add 1 to that power, that becomes 5/2. Divide by 5/2 is multiplying by 2/5. The last thing to do is to plug your u back in. And you can make that square root if that helps you, or if that looks better to you, if that's more aesthetically pleasing. I'm fine with you changing that to a square root sign. You could even make that the square root of the sine of x raised to the 5th power if you wanted to. It's a good thing about math. You can write it in a couple different ways. All right. got just a couple minutes. I'm going to try to show you how to integrate cosine squared of x. And I think that I can get through it because it's pretty easy. Just like the derivative of cosine squared would not be negative sine squared, the integral of cosine squared is not sine squared because of the whole u and du thing. Now, what we want to do if we have cosine squared is we want to apply that power reducing formula. So what was cosine squared equal to? 1/2 times 1 plus cosine of 2x. Right? You understand that? That's just a trig identity. So now that's 1/2 times the integral of 1 plus cosine 2x dx. What's the integral of 1? X. What is the integral of the cosine of 2x? Think about it. Cosine of 2x. I'm not taking the derivative. That's what? 1/2 sine of 2x. Remember, you bring out the reciprocal of the du? The u is 2x, the du is 2, so you bring out a 1/2 plus c, and I'm done. You can multiply the 1/2 back in if you want to. The integral of sine squared works the same way. Now, because of what we have to do if it's to the 4th power, we have to say cosine squared squared, and that's going to give us something else to work with. And that'll take a little bit longer. We'll start that on Monday.